Eighth graders, we're going to take a look at Unit 5, Lesson 4, Functions and Volume. Okay, so here's your warm-up. What do you notice and what do you wonder? I want you to pause the video for a hot second, resume the video when you're ready, and we're going to have a discussion. Okay, ready, set, go. All right, welcome back. So let's look and see what our first notice is going to be. So we notice that the distance from the starting line is on the x-axis and the time in seconds is on the y-axis. Now, isn't that interesting? Isn't it usually the other way around? Something to think about. Then I wonder if this is a race with the starting line and the time is in seconds. Are they running fast or are they running slow? That's a good thing to consider. Let's check out the next notice. There are two lines that are on the graph. One is going down and the other line is going up. I wonder why is that? Okay, and then I wonder is what could be happening with two lines that look like that? Something to think about, huh? The next notice is that we see that one of the lines starts at 72 seconds. So as you can see, start here at 72 seconds. And the starting line on the other line is at 0 seconds. Interesting. What does that mean? Something to think about. Well, I also noticed that two lines meet at about 200 meters right here. It looks like it's about 200 meters from the starting point at 38 seconds. What could be happening to create this graph? Is this graph possible? Something to think about. We also notice for each distance from the starting line, there seems to be two times except for 200 meters. And what else do we wonder? Well, we wonder what could be happening to create this graph. Also, I wonder what the title of this graph would be. Interesting. Hopefully you came up with some good notice and wonders to share with your teachers. All right, moving right along. So activity 4.2, equations and graphs of functions. What might this graph represent? I want you to pause the video and write down some ideas that you think. When you're ready, resume and we'll go from there. Okay, ready, set, go. All right, so as I come back and I read this, I see that on my y-axis, I see inches. And then on my x-axis, I see months, the time, okay? So this would be height in inches, and I see the time in months, okay? So looking at this, I can see that in 1 month, it has grown 15 inches, whatever this is. And then 5 months later, it looks like it has now grown, 30 inches. And then 5 more months later, it looks like it's gone 45 inches. So that's telling me that for every 5 months, this particular thing is growing 15 inches. Now, could it be a baby? Could it be a plant? Could it be a tree? Those who like to grow vegetables, could it be something that you're growing? It could possibly be. Who knows? All right, something to think about. All right, your next task says match one of these equations to each of the graphs below. So you have A, B, and C, and then you have these different equations going for you. D equals 60 times T, where D is the distance in miles you would travel, and T hours if you drove at 60 miles per hour. The next one is Q equals 50 minus 0.4 times D, where Q is the number of quarters and D is the number of dimes in a pile of coins worth $12.50. And then the next one is A, which is area, equals pi times radius squared, where A is the area in square centimeters of a circle with radius r centimeters. Go ahead and pause the video. Figure it out. When you're ready, resume the video and we will go from there. All right. Ready? Let's move on. So let's think about this. Let's think out loud. So this first equation, we have the distance equals 60 times the time, where D is the distance in miles that you would travel and T hours if you drove at 60 miles per hour. So on a table, it would look something like this. So obviously, if you don't go anywhere for 0 hours, you have traveled 0 miles. But after traveling 1 hour, if you're going 60 miles per hour, then how many miles would you have traveled? 60 miles. Y'all, you know what? I was so shocked when I learned this as a kid. I was like, oh, duh, that's why it's called miles per hour. Then what about 2 hours? After traveling 2 hours, you got 120 miles. 3 hours, you got 180 miles. So keep going. What happened when you get 10 miles? I'm sorry, 10 hours. And then you will be heading close to where Mr. G is from, because I'm from South Carolina, and it takes me at least 12 hours to get home. You do the math. If I drive 70 miles per hour, how far? How long would it take me to get home? How many miles would I travel? Something to think about. Okay. So this graph will start at 0, and it looks like it will go up at a constant rate. The reason why we know it's going to go up at a constant rate, because you can see the whole numbers there, 60, 120, 180. It's going up at the same rate. Okay. All right, let's check out the next one, where we have Q equals 50 minus 0.4 times D, where Q is the number of quarters and D is the number of dimes, and a pile of coins worth $12.50. Yeah, you got a lot of money. All right, let's check out the graph. So if you look at this graph, you're going to see dimes and quarters. So when there's 0 dimes, you have 50 quarters, because we have a total of $12.50. When there are 10 dimes, you have 46 quarters. When there are 20 dimes, you have 42 quarters. So this graph will start at 50 and then will decrease. Every 10 dimes, it will decrease 4 quarters. Every 10 dimes, it will decrease us 4 quarters. I wonder why. Why do you think that would happen? Can anybody tell us why? Maybe you know that 10 dimes equals $1 and 4 quarters equals $1. So if you got 10 dimes, then guess what? You don't need the 4 quarters anymore, right? I think so. All right. So that's how you have, 10 dimes here. That's why you end up with 46 quarters. All right. Let's go to the next one. So we have A equals pi r squared, where A is the area in square centimeters of a circle with the radius r centimeters. Let's look at this graph. You have, of course, the 0 is 0, because anything times 0 is going to give you what? 0. And then if you do pi times 1 squared, you're going to get 3.14 and so on. You can see that's a repeating decimal. If you do it again and just replace the radius with, instead of 1, put a 2, and then you have 4 times 3.14, you're going to get this answer, about 12. It looks like it's about 13 if you round up, right? And then here you have 3. When there's 3, you have about 28, because if you round down, it's about 28. So this graph will start at 0, and it looks like it will go up, but it does not look like at a constant rate, because look at it. It's not the same rate. It's going up this differently each time, and that's fine. Okay. So once again, now I want you to match each one of these equations with the graphs. Go ahead and pause the video. See if you can do that on your own, and you can just draw the lines and make the connection. Okay. If you have not already done that, but if you have done it, when you resume the video, we're going to check your answers to see if it matches with Mr. G. All right. Ready, set, go. Okay, welcome back. So let's check it out. So let's see what this first one is going to match with. So you have D equals 60 times T. Okay, so we're going to match that one with B. And I wonder why. So after 1 hour, I'll travel 60 miles. So if you go here to 1 hour, you go up, and there's about, boom, yeah, right there, about 60 miles. So you can see that. Okay, so that matches. For the next one, you're going to match it here. Because if you're starting off with 50 dimes, y'all see that? Y'all notice that? 50, and then you minus 4 dimes. Every time you get what? The quarter, 0.4, it's 40 cents. So you can see it's going down, it's decreasing. Since your slope is negative, because your slope is going down. So that's how you know that one matches with this one, okay? Because our y-intercept is 50 and our slope is negative. This is the only one that's actually negative. And this is the only one that has a y-intercept of 50. You see that point right there? That's your B, your y-intercept. And obviously, the last one will match with A. Very good, okay? Also, you can look at it and see that because the radius is squared, your graph looks a little bit different. It's no longer linear anymore. You see that? So that's a conversation you should have with your teacher. See, a linear graph, it goes in a straight line up like this or down like this, but never like this. So as you can see that it's curved a little bit, you can see that this one will definitely match with A. All right, very good. So now let's go ahead and label each graph based on what we know about the equation. So go ahead and pause the video, resume when you're ready, and we're going to check the answers to see if they match with Mr. G. Okay, ready, set, go. All right, welcome back. So the first one, obviously, our independent variable is going to be the radius, and our dependent variable is going to be the area in centimeters squared. For B, you're going to have the time and hours as the independent, and our dependent will be the miles. Okay, and then for C, we're going to have dimes for the independent, and our dependent will be our quarters. Okay, now what does this tell you about the situation? Label the corresponding point on each graph. Oh, I'm sorry, we skipped the whole question at the top. What is the output for each function when the input is 1? And what does it tell you about the situation? And label the corresponding point on the graph. So let's go ahead and label the points. Now, what do you think that tells you? What is the input for each function when the output is 1? So right now, if you want to look at an example like B, when the input is 1, after 1 hour, the output is 60 miles per hour. So that tells me that for every 1 hour that I travel, I have gone 60 miles per hour. So I want you to think about the same thing for A and C and have that discussion with your teacher. Okay? Now, find two or more input-output pairs. What do they tell you about the situation? Label the corresponding points on the graph. So go ahead and pause the video. Do the same thing from here on out. Okay? Ready, set, go. All right, welcome back. So let's take a look at what Mr. G has. So the first one, you see my table, and I have my radius is 0, area is 0. So y'all see the rule in the middle? All right, so now my radius is 1. So I'm replacing my r with 1 and squaring it, and then I get this answer. And then I replace my r with 2, square it, multiply by 3.14, I get this answer, and so forth. And that's how you see my point going up on the graph. Okay, you see it? It's increasing. Very good. Let's check the next one. So if I create my table, once again, put my rule, my distance equals 60 times, the time. So right now, when I'm going 0 hours, I have traveled 0 miles, so I'll start there. After going 1 hour, I'll travel 60 miles. I got that. And then after going 2 hours, I travel what? 120. And then after 3 hours, I'll travel approximately 180 miles. So you can see it's going up. Very good. All right, and last but not least, you can see here my rule when I plug it in. When I replace the D with all the input values I have here, you see my numbers here. So right now, when there's 0 dimes, I have 50 quarters. I start there. When there are 20 dimes, I have 42 quarters. When there are 40 dimes, how many quarters would I have? Hey, you got it, cuz that's right, 34. And then obviously, when I have 60, oh my bad, back it up here, y'all. When I have 60, then I will have what? 26 quarters. Very good. All right. So right now, this is the point where you're going to have a discussion with your teacher and your classmates. And this is what you will discuss. Where are the independent variables labeled on the graph? Where are the dependent variables labeled on the graph? And what do you notice the output for the graph 3 when the input is, move this out of the, oh, sorry, when the input is 1. Okay. So very good. I'm going to let you go ahead and talk this out with your teacher. Resume when you are ready. Ready, set, go. All right, welcome back. So once again, when the input is 1, we're going to check to see what are the independent variables, what are the dependent variables. So I said it earlier if you were listening or if you caught it. And also, you should have known this from my previous video when we talked about the independent variables and the dependent variables. So your radius is going to be your independent variable, and your area depends on the radius, okay? For this one, your hours is your independent variable, and your miles is your dependent because your miles depends on the number of hours you travel. So you don't know how many miles you're going until you know how many hours you travel, right? At a constant rate. And the same thing here for the dimes. The number of quarters you have will depend solely on the number of dimes you have. Okay. So therefore, your dime is your independent variable, and your quarters will be your dependent variable. All right. Awesome job. So let's check out 4.3. I know we got some track stars in the house. That's good. So my boy Karan was running around the track. The graph shows the time T he took to run various distances D. The table shows his time in seconds every 3 meters. Okay. So here we go. So let's look at question A, B, and C. A says, how long did it take Karan to run 6 meters? B says, how far had he gone after 6 seconds? And C says, estimate when he had run 19.5 meters. Go ahead and pause the video. Resume when you are ready. Okay? Ready, set, and go. Boop. All right, welcome back. Well, first of all, let's go ahead and do this real quick. Let me get my handy dandy laser pen. So right now, it says how long did it take Quran to run 6 meters? Well, if you come here to the graph and you go to meters, remember, read this. This is your meters. This is your time. 6, you go over, is about 2 seconds. Okay. So you can also see that on my table below. So it's about 2 seconds. All right, how far had he gone after 6 seconds? So if I come up here to 6 seconds and I go over, let's see what else I get. Hold on one second. Let me move this out of the way. So I come up with 2 seconds. Now for B, how far had he gone after 6 seconds? Go ahead and pause the video, see if you can figure it out, and then see also figure that one out as well while you're pausing your video. When you're ready, resume and we'll go from there. Okay, ready, set, go. All right, welcome back. So after 6 seconds, if you come up here and go over, you will see that they have gone approximately what? It looks like about 18 meters. And if you come down here, your time is below. You see 6 seconds and you see 18 meters, which is good. Okay. And for C, it says estimate when he had run 19 and a half miles. So if you come meters, I'm sorry. So if you come down here, you see 18 and 21. 19 is closer to 18. So if we go up a little bit there, it looks like he's going to be somewhere here, right? So what do you think it's going to be? So it looks like it's going to take him somewhere between 6 and 7 seconds, but closer to 6 seconds, right? So we're just going to say somewhere between 6 and 7 seconds. It could be 6.5 seconds. It could be 6.25 seconds. It depends. It's just somewhere in between there. So we can say between 6 and 7 seconds. Okay. All right. Very good. The next one, D says estimate how far he ran in 4 seconds. And E said is Quran times a function of the distance he has run? Explain how you know. So go ahead and pause the video, answer those questions. When you're ready, resume and we'll go from there. Okay, ready, set, go. All right, let's check it out. So estimate how far he had ran in 4 seconds. So we see that 3 and 4 is here. So 4 is here. 4 seconds. Look at it now. How far do you think he had run? So it looked like he had run somewhere between 12 and 13 meters. How do we know? Because if you were to follow that over, it looks like it's about here. So this is 12, and it's like it's closer to 12. So we're going to say between 12 and 13 meters. Okay. And is Quran time a function of the distance that he has run? Yes, Quran time is a function of the distance he has traveled. By reading the graph, you can use the distance he has traveled to find the time it took him to travel. And because you can do that, then this will be a function. Now, if you couldn't do that, it would not be a function. Something to think about. All right, so Priya is running once around the track. The graph shows her time given how far she is from her starting point. Okay, so as you can see, this is that funny looking graph again that you had earlier, right? Yes, it's back to see you again. All right, so let's check out A. A says, what was her farthest distance from her starting point? B says, estimate how long it took her to run around the track. And C says, estimate when she has 100 meters from her starting point. Pause the video, resume when you're ready. Okay, ready, set, go. All right, welcome back. So what was her farthest distance from her starting point? What was her farthest distance? It looks like it's about here somewhere. So we're going to say it's going to be 200 meters on the most right-hand side of the graph, because if you see that's 175, it's about 200 meters, somewhere right in there. Very good. Okay. Estimate how long it took her to run around the track. So if we look at this, how long do you think it would have taken her to run around the track? We're going to say about 75 seconds from the top left. Right now it says that's 72, but a little bit above that. So we know it's going to be approximately 75 seconds. From the top left point, we can see that it is when Priya is running back to the starting line. Okay. So that answered that question that we had earlier. It was like, why does graph look like that? Why? Because she's coming back to the starting line. Okay. All right. And C says estimate when she was 100 meters from her starting point. So when was she's actually 100 meters from her starting point? So 100 meters is about right here. So it looks like it's halfway between 12 and 24. So that was put us somewhere at about 18 maybe. So we're going to say about 18 seconds and 54 seconds up here. Okay. 54 seconds up here because you can see it between 48 and 60 right up in here. So we'll say about 54 seconds there. Awesome job. But hold on a minute, we're not done just yet. You have 2 more questions I need you to answer. Next one says estimate how far she was from the starting line after 60 seconds. And the last one says is Priya's time a function of her distance from her starting point? Explain how you know. Okay, go ahead and pause the video. Resume when you're ready. Ready, set, go. All right, welcome back. So estimate how far she was from the starting line after 60 seconds. After 60 seconds, so let's find 60 seconds. Where how far she was. So right here, it looks like she was about 75 meters. Okay, so we're gonna say she was 75 meters, and there's only one point on the graph corresponding to a time of 60 seconds, and that would be it. Okay, right there, 75 meters. All right, and is Priya's time a function of her distance from the starting point? And if you look at that, we're gonna say no, because the time is not determined by the distance from the starting line. Okay, here's some questions that I need you to consider. And this, you can have this discussion with your teachers in class. Each representation of a function presents information about the input and output of the function in different ways. Imagine we have a function with independent variables x and dependent variable y. How do we find the input-output pairs from a graph of function? What is something you won't see in the graph of a function? If the graph of the function contains the point 18 and 6, what else do we know about the function? So just please have that discussion with your teachers and enjoy it. Have a good time. I hope you guys learned something today, and I hope you enjoyed the video. Remember, I really appreciate all that you have been doing, and I look forward to seeing you in my next video. Have an amazing day. Until next time, take care.